Hi, I'm Caleb Holbert, a member of Stefan Selfeld's lab at HHMI's Genelia Research Campus. Today I'm going to be talking about Paintera, an annotation tool that we developed to improve upon the state of dense annotations of large 3D volumetric data. I'll be giving a brief overview of Paintera and then showcasing existing projects that are using it. Then I'll demonstrate a few of Paintera's unique features, including some exciting annotation tools. At the end, I'll mention some of the proposed additions and improvements we would like to see moving forward. So what is Paintera? Paintera is an image annotation tool with the goal of enabling productive annotation of large 3D datasets. Paintera is cross-platform and leverages JavaFX for its UI, ImageLib 2 for its data management, and Big Data Viewer for visualization. The typical workflow for Paintera is to load your image data, create or load a label image, and begin annotating. The main annotation method is the paintbrush, but there are additional tools which help streamline the annotation process. One of the key features is the ability to view and paint from any arbitrary reslicing of the data, to more easily annotate structures that are not axis aligned. Some of the features that are unique to Paintera among annotation tools are the ability to load images from cloud sources, generate meshes on the fly, process virtual images with little additional memory overhead, painting in non-orthogonal axes, and volumetric shape interpolation. Now before we jump into demos of some of these features, I'd like to show a project at Genelia that is currently using Paintera. Genelia's CellMap team is currently training machine learning models for segmentation of cellular organelles. They noticed that their models had difficulty segmenting organelles with large internal spaces. With previous annotation tools, annotating large volumes at high resolution was difficult. Paintera supports multi-resolution annotations and helps the CellMap team more quickly generate training data over larger volumes. This will allow the CellMap team to provide more training data at multiple resolution levels. The project takes advantage of the multi-scale label images and the non-orthogonal slicing to more quickly annotate internal spaces of large organelles, such as mitochondria and nuclei. Here's a glimpse of some of the annotations over mitochondria in liver tissue. You can see the annotations in blue, which represent the internal space of the mitochondria. The real-time mesh visualization in the bottom right helps the annotator to verify the annotation in 3D. The other three slices that you see are orthogonal views of the same area in the data. Next, you'll see a similar set of data containing annotations of nuclear volumes. Here you can see rotating through the slices to show arbitrary rotations into the annotations. Now that we've seen some of the ways Paintera is being used in practice, I want to demo some of the functionality that Paintera provides. I'll start by loading data into Paintera. Of course, we support local data stores, including N5, HDF5, and XAR backends, but it isn't always convenient to have your data sources locally. Paintera also supports loading from cloud sources, including AWS and Google Cloud. Our collaborators in the CellMap project team at Genelia have developed OpenOrganelle.org. Many high-resolution EM images are publicly available to be streamed on demand from AWS. Paintera makes it possible to work with these large data without needing to download or to store them locally. Here, I'll start by opening the dataset. I'll paste the AWS link that we want, and you'll see a bunch of data sets here. I'll select one that's around 250 gigabytes in total, specify that it's raw data, and what you'll start to see is the low resolution data being loaded in first. As you move around, you'll see it loading in higher resolution data as it prioritizes what you're looking at any given moment. You'll see here that chunks that are lower resolution will become higher resolution as you stay there. And as you zoom out, it will refer to lower resolution. Here we can load a couple data sets for labels. So first we'll look at a nucleus segmentation and specify that it's a label set. It'll ask at first, because you haven't seen this data set before, if you'd like to generate meshes on the fly. This is useful for generating 3D meshes and visualizing the labels. Here you'll see we'll select the nucleus label, and you can see it generating the meshes starting from the areas closest to you and working its way away. We'll then load mitochondrial data, also a label set, to see how the labels overlay with the nucleus label. Again, we haven't seen this before, so it'll ask if we want to generate the meshes on the fly. And we'll select all of these labels, and you can see them start to generate as we go over and look at them. Now let's look at another data set which emphasizes some of Paintera's unique features. Here we're looking at a neuron that doesn't neatly align with the orientation of the data. So using keys, keyboard shortcuts, and mouse keys, we can move into the correct orientation to paint the volume that best or is oriented to the structure. And you can see we paint at a few slices here, including painting multiple layers at a time with depth if you desire. And you can touch up around the edges where you see that mistakes are made. Then we can go back into the data's orientation, and you can see that that is in fact in an axis not aligned with the data. Okay, so now we're going to look at another neuron, And this neuron, what we're going to do is do a quick skeleton outline of this slice. And this is to emphasize the fill tool. So there's a fill tool that allows you to fill in internal slices that you've skeletoned out. So another feature that Paintera has is virtual images. Virtual images are generated on the fly by processing existing images without requiring the additional memory footprint. Currently, there's a threshold source, which allows you to provide a threshold of raw data, and a connected component source, which allows you to select two images and intersect one into the other. Where the images intersect, the component in this second image will be labeled. So overlaid on this electron microscopy image, magenta and green show the predicted distance from synaptic clefts. We first have created a virtual threshold image over the synaptic cleft distances to get an idea of the area around the synaptic clefts. Then we've created a connected component source between the synaptic cleft threshold image and the neuron label image. This has the effect of showing the synaptic clefts that are touching a given set of selected neurons. Here you can see the synaptic clefts that are touching this blue neuron in white. You can hone in on a particular area, for example, by clicking on the mesh. And then, as you see, we slice through and rotate through this area to see how this cleft interaction looks from various different angles. Last, we can turn off the mesh visibility so you can see all of the clefts that are touching this neuron. Another powerful tool is shape interpolation. On the top right panel, you'll see that I'm painting in a single slice through this image. Later, I will move through this image and then slice and then paint another image at a different slice. No, I did not paint anything in between, just these two slices separated by some distance. On the left-hand side, you'll see two views from two orthogonal views, and you'll see that it's been filled in. The volume has been filled in between the two slices that I painted. I'll continue to do this and paint more slices, and you can see as I do this that the volume between these slices on the left gets filled in. And you can see sometimes as I'm going, I'll do some painting and I'll do some refinements on the fly. For example, right here, I notice an area that doesn't quite have the right fill. I'll go back and fill that in. And then as I'll move forward, you can continue to paint slices, and you can do multiple slices for this. And then ultimately, when you're happy with it, you can submit that and you generate a mesh, of course, and you can view the result of the interpolation in 3D. And it's a really nice starting point to be able to refine from to get a large volume, especially for structures that are shaped like this. As we continue developing Paintera, we want to make sure to provide a robust tool that can be used for effective annotation of large volumetric datasets. Some of our near-term goals are to increase the label lookup performance by utilizing a database backend, as well as adding more painting modalities and more opportunities to take advantage of virtual images. We're also aiming to improve our release process to make installation and updating as seamless as possible. Of course, Paintera is an open source project, and if anyone is interested in working with Paintera from a development perspective or has issues to report, please check out the GitHub page and feel free to reach out. As with all open source projects, Paintera benefits immensely from an engaged and active community, and I look forward to seeing more users and contributors as we continue to develop exciting features. And last, thanks to the rest of the Southfield Lab and the CellMap team for their contributions to Paintera. In particular, thanks to Allison for providing her Paintera annotations for this talk. And thank you all for coming, and I hope I've convinced you to consider Paintera for your annotation projects.